Hi, this is Dr. Hayek. In this video, I'm going to talk about molecular orbital theory. I will start this video by briefly discussing the quantum mechanics. Now, we know that Bohr's model for hydrogen, it doesn't work for other elements. So Schrödinger and de Broglie, they came out with a model where they suggested that for every electron corresponds a wave function. Now, they also said that an electron moves around the nucleus as is represented in this scheme in here. So an electron path would look like a standing wave. Now, I'm not going to discuss quantum mechanics in this video, but I'm going to say that when two atoms meet to form a molecule, the electrons will meet in a similar way to two waves. Now, if two waves meet in a parallel or in phase, we call this constructive interference, and the result will be a bigger wave. However, if two waves meet out of phase or antiparallel, we call this a destructive interference, and they will cancel each other. Now, why this is important for our today's topic? Now, let's consider two 1s atomic orbitals that they will overlap. If they overlap in phase, they will give a bigger orbital where it's called the molecular orbital. And in this molecular orbital, we can see that the electron density is concentrated between the two nuclei. However, if the atomic orbitals overlap out of phase, the result will be a plane which is called a nodal plane that's going to exist between the two nuclei, where the two electron densities are pushed away of the center, and this nodal plane cannot contain any electrons. Now, the first one that was resulted from the in-phase combination, where the electron density is concentrated around the nuclei, it's called bonding molecular orbital, and the one that contains a nodal plane, it's called an anti-bonding, so it doesn't favor the bonding of electrons, so bonds will not form. Now, why do we need to know this? If we take a look on the hydrogen molecule, where it has one s orbital per each atom, so one s orbital will combine or overlap with another one s orbital. They might overlap in phase or out of phase. If they overlap in phase, it's going to form the H2 molecular orbital that we call the bonding molecular orbital. So this is the orbital that will favor bonding within the molecule or between the two atoms. Now, if the two atomic orbitals, they overlap out of phase, so they're going to form the anti-bonding molecular orbital, and therefore this orbital will not favor bonding. Now, as you can see, the bonding molecular orbital is lower in energy than both atomic orbitals, and the anti-bonding molecular orbital, it's higher in energy than the atomic orbitals. Now, we represent this scheme by squares like this, so where we have the 1s atomic orbitals, and for the molecular orbitals, we call them sigma with the subscript 1s, and for the anti-bonding, we call it sigma star 1s. So now if you consider the hydrogen atoms, every hydrogen atom will have one electron. Now these electrons will fill the sigma 1s orbital, and therefore the H2 molecule will have two electrons in the sigma 1s molecular orbital. Now, in molecular orbital theory, the stability of a covalent bond is related to its bond order. What is bond order and how it can be measured? Bond order is equal to half of the sum of the bonding electrons minus the sum of the anti-bonding electrons. We are going to see further example of the bond order along this video. So now, if the bond order is equal to 0, it means the bond it cannot form. If the bond order is equal to 1, it means I have a single bond. If the bond order is equal to 2, it means I have a double bond. And if it's equal to 3, I will have triple bond. Now, since molecular orbital theory, it deals with molecules that they have odd number of electrons. So having a bond order of a 1/2 or 3/2 or 5/2, it's also possible. Now, any bond order that's higher than 0, it means that the molecule is stable and it can form within certain conditions. So let's take a look on the following example now, which is helium. And let's check if the diatomic helium is a stable molecule or not. So if we consider that we have 2 electrons for each helium atom, now we will have a total of 4 electrons. Now these 4 electrons will fill the 2 molecular orbitals for helium molecule. Now we will have 2 electrons in the sigma 1s and 2 electrons in the sigma star 1s. Now if we find the bond order for He2, we can see that the bond order is equal to 0 because we have 2 bonding electrons and 2 antibonding electrons. A bond order of 0 means that a bond cannot form between the 2 He atoms, and therefore He2 molecule, it's going to be an unstable molecule and it will not form. However, if we consider now the He2 plus ion, now we have 2 electrons for the helium atom and 1 electron for the helium ion. And combining these 3 electrons, we will fill 2 electrons in the sigma 1s and 1 electron in the sigma star 1s. If we find the bond order, we can see that we have 2 bonding electrons and 1 antibonding electron, and this will result in a bond order of a half. Now, as I mentioned before, any bond order higher than 0 means that the molecule or the ion can form and it's stable. So we can see that He2 plus, it's a stable molecule at the gaseous state. Now in a similar way, I can further extend this to period 2 elements and looking at Li2 and Be2. Let's first check if Li2 molecule is a stable molecule or not. So in a similar way, we have 3 electrons for lithium. Both will have 6 electrons. Now 6 electrons will fill sigma 1s, sigma star 1s, and in a similar way to 1s orbitals, we can also find the same thing for 2s orbitals, and we will have 2 electrons in the sigma 2s. Now looking at the bond order, we have 4 bonding electrons and 2 antibonding electrons. So that's going to give me a bond order of 1, which is greater than 0. Now this is going to be a stable molecule then. Diatomic lithium will only form at the gaseous state. Now beryllium, however, each beryllium will have 4 electrons. So the 8 electrons will fill all the molecular orbitals, the sigma 1s and sigma 1s star, and the sigma 2s and sigma star 2s. So the bond order will be 4 bonding electrons minus 4 antibonding electrons, and the bond order is going to be 0, and therefore this is an unstable molecule. Now, in a similar way that we discussed the orbitals overlapping in an s atomic orbital, we can also discuss the same thing for a p atomic orbital. Now remember, p sublevel extends over the xyz axis, and therefore we have a px and py and pz. Now we will consider that the pz orbitals will overlap in a horizontal way, and therefore we will see that for the pz, when 2 pz orbitals overlap, they can also overlap in phase or out of phase, and they can form the bonding and anti-bonding orbitals. Now since they are overlapping in a horizontal way, they are going to form a sigma. Now we will call that sigma 2p and sigma star 2p. Now for the px orbitals, they are going to overlap in a parallel way, and therefore they are going to form molecular orbitals that the electron density is distributed above and below the plane, and therefore they're going to form pi bonds, and that's why we call these orbitals as pi 2p and pi star 2p. We have another pi 2p and pi star 2p that they also can form from overlapping of py orbitals. So now as you can see, we can illustrate this in a similar way to what we did with the s orbitals and get the following scheme. So now you can see that I have a sigma 2p and a sigma star 2p, and I have pi 2p, 2 orbitals, and pi star 2p, 2 orbitals as well. Now note here that I'm combining 3 atomic orbitals with other 3 atomic orbitals. So it's a total of 6 atomic orbitals. They will result in 6 molecular orbitals. So now that I showed you how the molecular orbitals can form from the s atomic orbitals and the p atomic orbitals, so now we can apply this to the homonuclear diatomic molecules from the second period of the periodic table. So the general scheme will look like this. We will have the atomic orbitals that they will overlap to form the molecular orbitals. Now, experimentally, we found that this scheme applies only to oxygen, fluorine, and neon. Now, why is that? What about the rest of the elements? Now, in different molecules, it was noticed that there is an overlap between the 2s orbital of one atom and the 2p orbital of the other atom, and therefore, this will result in a change in the energy level of the sigma 2p and the pi 2p. So the sigma 2p will become at a higher level of energy, and the pi 2p will be at a lower level of energy compared to the previous model that we represented. And now, experimentally, it has been shown that this model fits more the B2, C2, and N2 molecules. So now we are going to apply this to these different molecules and check whether they are stable to form or they are not stable, and also discuss a little bit the bond order and their magnetic property. So let's start now by discussing the oxygen molecule. Now, we all know that oxygen can form diatomic molecules, and we know the Lewis structure, and we know that there will be a double bond between the two oxygens. So let's apply our model now to see if we can confirm all these observations or this knowledge. Now, each oxygen has 8 electrons. These 16 electrons will start to fill the molecular orbitals from the lowest energetic to the highest energetic. So therefore, I'm going to fill the sigma 1s and sigma star 1s, then the sigma 2s and the sigma star 2s, then fill the sigma 2p and the pi 2p. So far, I have used 14 electrons. The remaining 2 electrons will be, according to Hund's rule, each electron will fill one of the pi star 2p. And now I can calculate the bond order. So the bond order is equal to 1/2 multiplied by, I have 8 bonding electrons and 4 antibonding electrons, and therefore the bond order is equal to 2. Now that's good because bond order of 2 means that I have to have a double bond, and this confirms the Lewis structure that we know. Now, regarding the magnetic property, now this is another topic where we say that if a molecule is a paramagnetic, this is when it has unpaired electrons, like oxygen in here. So oxygen is a paramagnetic molecule. However, if all the electrons in the molecule are paired electrons, the molecule is called diamagnetic, and we are going to see examples to this. Now let's discuss in a quicker way fluorine. Now each fluorine has 9 electrons, so I have a total of 18 electrons. If I fill the electrons in a similar way to oxygen, I will end up having 2 electrons in each pi star 2p. And if I find the bond order, it's going to be 8 bonding electrons minus 6 antibonding electrons, and the bond order is going to be equal to 1, which also fits the Lewis structure that we know, where we have a single bond between the 2 fluorine atoms. Now, as you can see in here, all electrons in the fluorine molecule are paired electrons, and therefore that's going to be a diamagnetic molecule. Now, what about neon? Does it form a diatomic molecule? And is it stable? So in a similar way, neon has 10 electrons each atom. These 20 electrons are going to fill all of the molecular orbitals. So the bond order is going to be half multiplied by 8 bonding electrons minus 8 antibonding electrons. And therefore the bond order is going to be equal to 0. And thus it means that there's no bond that can form between the two neon atoms. And therefore an E2 is an unstable molecule. Now if you look at the different scheme that fits the other molecules than oxygen, fluorine, and neon, where we have the sigma 2p is at a higher energy level than the pi 2p. Now for B2, there's this possible lowest structure where we have only a single bond. Now the reason I did this, there is another lowest structure that's reported where you have triple bond between the two borons. So like this you have 6 electrons around each boron. And anyways, that is not our topic for today. So I want to check whether this lowest structure corresponds to the bond order that I'm going to get. So every boron has 5 electrons, and these 10 electrons will fill the sigma 1s, sigma star 1s, sigma 2s, and sigma star 2s, and they will fill the pi 2p orbitals with 1 electron each. Now, I forgot to mention something here. I'm always looking at the valence electrons and I'm ignoring the 1s orbitals. So because the bonding happens only at the valence level, it doesn't consider the core electrons. So now in this case, I have 4 bonding electrons and 2 anti-bonding electrons, and the bond order is going to be equal to 1, which suggests a single bond between the 2 boron atoms. Now what about the magnetic property? As you can see, boron, or B2, which is a stable molecule, has 2 unpaired electrons, and therefore it's a paramagnetic molecule. Now what about C2? Each carbon has 6 electrons, and therefore I will have a total of 12 electrons that they are going to fill the sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and the pi 2p. And therefore, the bond order will be 6 minus 2. Again, looking only at the valence electrons. And the bond order is going to be equal to 2. And that's why I have double bond between the 2 carbons in C2. And it's a stable molecule. And it doesn't have any unpaired electrons. And thus, this is a diamagnetic molecule. The last molecule I'm going to discuss in this video is the nitrogen. And we all know that nitrogen molecules exist under their diatomic form. So let's confirm that with our model. Each nitrogen has 7 electrons. These 14 electrons will fill the sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, and the pi 2p and the sigma 2p. Now the bond order will be 8 minus 2 multiplied by half, and that's equal to 3. And we all know that the lowest structure of nitrogen has triple bond between the 2 nitrogens. So this is also confirmed. Now looking at the electrons, we cannot see any unpaired electrons for nitrogen, and therefore nitrogen is a diamagnetic molecule. I hope this video was helpful to you. So please like, share, and subscribe. And I'll see you next time.